This video is on the transverse Doppler effect. It's really a special case of the angular dependent Doppler effect, but there are some hidden surprises, and so we'll be going through the derivation in this video. And so, of course, the Doppler effect was proposed by Christian Doppler in 1842, and so in 1842, and for instance, the way that you visualize that is in terms of an emitter, and I'm just going to have sort of at time t equals 0, I'm going to have a plane emitter, and let's say that it emits a wave front, so at time t equals 0, it emits a wave front. And then what we do is we go to a time which is one period away. So then when t equals capital T, and I'm going to say t0, so that's going to be the natural emission time. And so the object is moving, let's say, in the positive x direction. And so that has moved a distance of v times t0. And at time t equals 0, it had actually emitted a wavefront, which is traveling at the speed of the wave, and so that's going to be faster. And so that means that at this time t equals t0, that the wavefront will have moved to about here. And so we can say that this is going to be equal to c times t0, so that's the speed of the wave, and we'll just go ahead and take light. And so we've got c times t0 moving in that direction, and then in the same time we've got the object has moved by an amount vt0, and then because it's one period, then it's emitting that next wavefront. You can either think of these wavefronts as pulses occurring at a very regular time of t0, or you can think of it as one peak of the wave and then the successive peak of the wave. And so what that means is that because this has moved, that the wavelength then that's going to be detected off in this direction, so we're going to have some kind of a detector off here, the wavelength which is going to be detected is going to be shorter than the natural wavelength, because the natural wavelength is actually given by this expression here. So ct0, so the speed of the wave times the period of the wave is equal to the wavelength. And so we see definitely that lambda is less than lambda naught. And so we can then put the math to this. And so the way that this looks is that lambda is equal to the full distance ct0, but then we have to subtract off this vt0. And then what I'll do is I'll bring out, and so I'm using the fact that ct0 equals lambda, so that means that pulling the ct0 out front, I get a lambda naught, and then we'll distribute that on a 1 minus v over c. And so then that is the new wavelength that is observed as the emitter is moving towards the receiver. And so the wavelength is smaller, so this is what's known as a blue shift. And by the same math, we can actually reverse everything, and so then all we have to do is put a plus minus, or actually I guess what maybe might be, we'll call it minus plus. Okay, so minus when it's moving towards you, that's the blue shift, plus when it's moving away, that would be the red shift. Now this is in the direction of motion. So obviously there's going to be a Doppler effect off at some angle as well. And what we're going to call this effect is really a foreshortening. And so let's just call this foreshortening. And specifically when it's moving towards the receiver. And so we have this foreshortening effect. And that effect then will vary as cosine of theta. And so if I have the object and it's moving in this direction, but let's say it's emitting waves off at some angle theta, then obviously there's going to be a cosine theta that goes in here. And so the Doppler effect is going to vary as cosine theta. And so we're going to have positive cosine thetas when theta is close to 0. Cosine theta is going to be negative when it's close to pi, and that's in the back direction. And obviously if theta goes to pi over 2, then there's no foreshortening at all. And so there'd be no, in this non-relativistic case, there'd be no transverse Doppler effect. So that's what we really want to study now, is what happens when we bring in relativity. And so let's consider the transverse Doppler effect in the case of relativistic effects. So let's bring in relativity. And what's going to happen is that the foreshortening is still going to happen. One limitation is going to be that objects have to travel less than the speed of light. And so they're going to be limited in their speed to the speed of light. And there will be foreshortening, just as we calculated for the non-relativistic case. But now there's going to be time dilation. And so the emitter, because it's moving at relativistic speeds, will have time dilation. And so if it's emitting, let's say, a steady pulse, then the duration of the pulses will stretch, they'll lengthen. Or if it's an emission of, let's say, light from an atomic transition, then that light will actually become redshifted by just time dilation alone. That just the atomic clock riding on this relativistic spaceship would actually be slowing down. And so we want to include that as part of the calculation. So it means that we have the two effects. So for relativistic effects, we still have foreshortening, but we also now get time dilation. And that's really what makes it relativistic. Okay, so setting up the configuration for that. So I have an object which is moving in this direction. And so then at a certain time, we'll say time t equals 0, it emits a photon. Now this is in the lab frame or the receiver frame. So the receiver stationary, the source is moving. And so I'm going to call this theta naught. And it's at time t equals 0, it will have emitted a pulse, let's say. And so then at some later time, and we're going to go ahead and let this move a distance. And so this will have moved a distance vt. The pulse will have moved to here. And then the next pulse that's coming is going to be coming from there. This distance is vt cosine theta 0. This distance is c times t. And then this distance down here was v times t. And so we have everything we need to know. In fact, let me actually also write down that basic formula. That ct0 is equal to lambda 0. And we need one more equation, which is that t is going to be time dilated. So t naught is the natural emission time, and then gamma is the gamma factor. And so gamma is equal to 1 over the square root of 1 minus beta squared, where beta is equal to v over c. Okay, so now we have everything that we need for the math. And so we have that the wavelength, which, by the way, let me draw that too. So the wavelength is now this distance. Okay, so that means that we've got lambda is equal to c capital T minus v capital T cosine theta naught. And then we'll just start to throw in the fact that t goes as gamma t naught. And so let's put in a gamma t naught. We'll distribute that out front. So I get a c minus v cosine theta naught. And then let me go ahead and divide through by c, and then the t naught will actually become a wavelength. It's the natural emission wavelength, but this now becomes 1 minus beta cosine theta naught. Okay, and let me just go ahead and write out all the beta dependencies in this. So this is equal to lambda naught, and I've got in the numerator a 1 minus beta cosine theta naught, and in the denominator I've got the square root of 1 minus beta squared. Okay, so that's now the formula for the angular dependent Doppler effect. Right, so this is the angular dependent Doppler effect. And so we can already start to do some special cases. So let me just start with forward emission. All right, so forward emission, that's when theta naught is equal to 0. And so I can just plug right in. So it's just lambda is equal to lambda naught. I've got a 1 minus beta cosine theta naught, but cosine of theta is 1, so this just becomes a 1 minus beta on top divided by, now I'm going to actually write out the 1 minus beta squared. It actually factors out into a 1 minus beta and a 1 plus beta. And so then you can see that the 1 minus beta in the square root will actually give me the expression with the whole thing under a square root of 1 minus beta over 1 plus beta. Okay? And so then that is the blue shift that is caused by moving, by having the receiver in the direction of motion. And then we can do a backward emission. So backward emission. Which is theta equal to pi. And I can just plug in the same thing I did before. This becomes lambda naught. Now it's not 1 minus beta, it's actually 1 plus beta on top. I still have the square root of 1 minus beta, 1 plus beta. And so now the 1 plus beta, actually, we cancel one square root factor there, so this becomes lambda naught. And then the square root of 1 plus beta over 1 minus beta. Okay, and so then that is the red shift, and so the source is actually moving away from the receiver in that case. So now we want to go to the transverse effect, because it's the transverse effect that we were most interested in. So the transverse is easy, and so the transverse we have that theta naught is equal to pi over 2, and so cosine of theta naught is actually equal to 0. And so then it means that I can just write just directly lambda is equal to gamma lambda naught. Okay, and so then gamma is always greater than 1, and so the lambda gets longer. So this is a redshift. Now what's important about this redshift is this is specifically time dilation. So this gamma is coming exactly from the time dilation. If you remember the non-relativistic, so the Doppler formula, there was no transverse frequency shift. So here we actually see that there is a frequency shift, and it's caused exclusively by time dilation. And in fact, Einstein actually pointed this out. So in 1905, so Einstein in 1905 wrote his classic paper on relativity, and one of the things that he derived actually was the angular dependent Doppler effect. But then in 1907, he actually proposed that if you could look at light emission from ions in a perpendicular geometry, that you would see the direct effect of time dilation. Because in 1907, there were a lot of people who still didn't believe Einstein's theory of relativity. Lorentz had actually come up with this kind of funny theory about how electrons would sort of shrink in the direction that they were moving. And a lot of people still subscribe to that. And in fact, it was Stilwell and Ives who finally did this experiment of looking at light emission from ions at right angles. And this was in 1938. And so they saw the effect. They actually saw the time dilation effect, sort of vindicating Einstein. And yet, in their paper in 1938, they were still actually talking in terms of Lorentz's outdated theory. And so they thought they had actually confirmed Lorentz's theory, when in fact what they had really done was confirmed Einstein's theory, and the fact that time dilation wasn't just an apparent effect of special relativity, it was a real effect. I mean, so clocks really do slow down as they move fast, and it's not just an apparent effect, it's an actual real physical phenomenon. All right, so that's the transverse Doppler effect viewed one way. All right, so it turns out that there's an alternative, and this alternative actually is important when you work with problems, let's say, of circular motion. If you have sources moving in circular motion, or if you have a receiver moving in a circular orbit around a source. And so there's actually another way of defining a transverse effect, and so let's look at this alternative. And this is where there's kind of this hidden surprise, and so we end up getting something which is a little counterintuitive. All right, so first I have to set up the geometry for this, and so we're going to have the object moving along the x-axis, and then we'll take the y-axis here, and so it's going to emit at some angle theta naught to a receiver point. And so then this is c times t. Now, at the moment that the receiver detects the photon, it's actually making an angle of theta 1 to where the object has now moved to. So in other words, at the moment that the receiver receives, the object is no longer where it was emitted, or emitted the photon, it's actually moved to this new location. And so this is obviously velocity times time, and we're going to call this script L. All right, so we've got this new angle theta 1. And so it's the angle to the object at the moment that the photon is detected at the receiver. So what we have to do is consider this height h. And so we're going to write that as ct sine of theta naught, but it's also equal to script L times sine of theta 1. Okay? And then we're going to use the law of cosines. So the law of cosines says that we've got v t squared plus c t squared minus 2vc t squared cosine theta naught is equal to L squared. All right, so let's go back to this equation here. So let's write this in terms of sine theta 1. So we've got sine theta 1 is equal to ct sine theta 0 divided by the script L. And so that means that we're going to be dividing by a square root. So it's going to be ct sine theta 0 divided by the square root of all this stuff of, vt squared plus ct squared minus 2vc t squared cosine theta, theta naught. Take a square root on that. And so let's just simplify that by dividing through by ct, and what I just get is the sine theta naught, and the c's and v's turn into betas, and so I've got a 1 plus beta squared minus 2 beta cosine theta naught. Okay. All right, so that's kind of ugly, but we're going to take the very special condition. So let's say theta 1 is equal to pi over 2, and that's why this is an alternative on the definition of the transverse Doppler effect. So in other words, we're saying that, okay, at the moment that the photon is received, the direction to the object at that moment is a right angle. It gives us the right angle. And so that means that what I can do is rewrite the fact that that sine of theta 1 is obviously going to be equal to 1 in that case. All right? And so let's work on that. All right? So what that's going to give us is sine theta 1 is equal to sine theta 0 divided by square root of 1 plus beta squared minus 2 beta cosine of theta 0, and that has to equal 1. And so I can rewrite the whole equation now as a sine squared theta naught, just multiplying or squaring everything and multiplying through by the denominator. So sine squared of theta naught is equal to 1 plus beta squared minus 2 beta cosine theta naught. And what I can do is I can actually look at the fact that that 1 minus sine squared is actually a cosine squared. And so I would actually get that a 0 is equal to a cosine squared theta naught minus 2 beta cosine theta naught plus beta squared. Okay? And then what I'm going to do is just say that x is equal to cosine of theta naught. And I now have just a simple quadratic equation. I've got that x squared minus 2 beta x plus beta squared equals 0. And so we can just plug that into the quadratic formula. And so the solution is going to be x is equal to 1/2 So minus b is going to be 2 beta, and then plus or minus square root of b squared, which is going to be 4 beta squared, minus 4 times a, which is 1, times c, which is beta squared. So the thing under the square root actually goes to 0. And so lo and behold, this is actually beta. Okay. And so it means that this is going to be equal to cosine theta naught. So cosine theta naught equals beta. So a very simple expression for cosine of theta naught. Plugging that now into the formula for the Doppler effect, and I have that lambda is equal to lambda naught. And then I have a 1 minus beta cosine theta, but that's going to be beta squared. And then divided by the square root of 1 minus beta squared. And so that means that I get a lambda naught times the square root of 1 minus beta squared. Okay, and in fact, this is lambda naught over gamma. And I just want to emphasize that, so this is a alternative definition of a transverse effect, and I've got lambda naught over gamma. And yet, if we look back here, to this one, we look here, we actually had the opposite effect, right? So here we've got the transverse when theta naught equals pi over 2, I've got lambda equals gamma lambda naught. And now I've got that lambda is equal to lambda naught over gamma, okay? So I actually get a red shift in one definition of a transverse effect, and I actually get a blue shift in the other. And so this is a blue shift here. And so whenever you're confronted with this question of, well, what do you do if there's two definitions? Well, the answer is always compromise. And so the compromise actually leads to a really simple result. So compromise. All right. So the compromise looks like this. I actually want to have an emission and a reception, and at the time of the reception, the object has moved to this position here. So while this is theta 1, I want this actually to be theta 0, and this is theta 0. And so I get a purely symmetric case. And so I have that, that theta 0 plus theta 1 is equal to pi. And so if I use that as my compromise, what I'm really doing is saying that lambda is just going to be the compromise. So it's just going to be lambda naught over 2, and it's just going to be gamma plus 1 over gamma. And so there's the, lambda naught gamma in the one case and the lambda naught divided by gamma in the other case. Well, just a little bit of math, this becomes 1/2 2 minus beta squared over square root of 1 minus beta squared. And here, I'm going to do a Taylor's expansion. Let's go ahead and assume that we're moving at slow speeds. And so this becomes, and there's a lambda here. So this becomes lambda naught over 2. And then I've got a 2 minus beta squared. I'm going to do a Taylor's expansion down here. So under that square root, I'm going to turn this into a 1 minus 1/2 beta squared. Now, divide the top by the factor of 2, I get lambda naught. And I get a 1 minus beta squared over 2 divided by 1 minus beta squared over 2. And in the low speed limit, this just becomes lambda naught. And so, in fact, with this compromise definition, we're back to the simple result that the transverse effect actually vanishes. But in this case, it's actually the average between the two definitions for the transverse effect. What's happened here is that the foreshortening has actually canceled time dilation, and that's why we get this very simple result that is just simply lambda 0. And so that's sort of the inside workings of the transverse Doppler effect.